Hello. Good afternoon, everyone. And thanks for coming. Also, this is our final lecture, and hopefully everyone started to enjoy the beautiful summer. But before that, we still need to address a little bit issues. That is the finals. Yeah, I think the major topic today is just to give a review, and also I'm trying to give you some information and confidence about final exam. It's not hard at all. And the problems will be very similar to the practice problems we're shown here. I believe you guys have seen this because we made this public in the Canvas, right? We also released the solutions. We just want to walk through those problems and to give you the sense of what kind of problems, what kind of topics we would like to show that in the final exam. And first, we want to state again. So you can bring one sheet of paper. I mean, typically A4 paper. You cannot bring a big poster. That's not allowed. Yeah, just one A4 paper and print it out, right? You cannot bring iPad saying, okay, this is my paper. It's not. Yeah, so just, I mean, write down whatever you think is useful that might help your final. Feel free to write it down and print it out and bring that piece of paper with you and do the final exam. And you can bring you can bring calculator, but most likely it won't be useful because we're not interested in asking you to hit the button and give me like 3 effective digits. You can write it down in a fractions, whatever form you like. And the exam will be next, which I believe is next Wednesday, April 30th, from 3:30 to 5:30 on this classroom. So please come here in person. We don't have like online exam. Make sure you join here, and then our TAs will hand you the papers, and everybody just spend your time finish the problems and handing not only the exam paper but also your cheat sheet. Okay. And I think that's basically all about the schedule of the final exam. Any question? Okay. Yeah. So yeah, I would like to briefly mention what kind of I mean, what's the coverage? It will cover all the topics we have discussed so far, except the hypothesis testing, because hypothesis testing only spend like 1 lecture and a half talking about that, and then we haven't assigned any homework problems on that. So we don't think it is fair to let you guys to prepare for that. That means like we're gonna start from the definition of the events, way up to the confidence intervals, right? So which we discuss what is random events, what's the probability, what's the rules to calculate the probability of the events, right? How do you calculate the probability of joint events, right? And what's the definition of independence between different events? What is the conditional probability of one event conditional on the other event? Okay. And then we proceed to the random variables. And the random variables are essentially a mapping from sample space to some real space, right? So talk about discrete random variables, continuous random variables, right? Random variables are not random, no variable, it's just a mapping. Then we'll talk about the probability mass function for random variables, probability density functions for continuous random variables, right? And you need to know the most commonly used random variables, their distributions, as we discussed in the class. For example, binomial distribution, right? And Bernoulli distribution, binomial distribution. Bernoulli distribution is like you toss a coin and you tell what's the likelihood, what's the chance that you see heads up, tails up, right? Binomial distribution is like, okay, you toss the coin for 30 times, you tell me how many times in total you're going to see the heads up. And then like geometry distribution, right? It's like you keep tossing the coin until you see the first time you heads up, right? How many tossing you're going to use, right? So they're all connected. And parental, and then for continuous distribution, I believe the most important distribution is the Gaussian distribution. Again, you don't need to memorize the PDF, probability density function, but you do need to know what is Gaussian distribution, right? And exponential distribution and parental distribution, right? And you need to know their concept. Perhaps we're going to ask you, what's the expectation of a Gaussian distribution? What's the variance of Gaussian distribution? You should know that. And then we'll talk about the confidence intervals, right? And we start with samples and statistics, right? It's like, okay, I'm gonna observe the real world and look at the values of those random variables, right? And because those quantity of interest, like raindrops, like temperature, like stock price, they're changing every time, right? Changing every second. So this observation will not be the same as the next observations. That's why it's called random variable. So we want to collect a collection of the values of random variables, which we call sample, right? And we want to calculate something under the sample to estimate the parameter of distributions. For example, if I assume the stock price follows some Gaussian distribution, I would like to know what's the mean, what's the variance, and what should we do? And usually we're gonna collect a set of samples for this Gaussian distribution. Then we'll calculate sample mean and sample variance, right, as estimation. That brings a problem, right? So first, the function of those samples are still random variables, right? That's very, very important. Otherwise, you won't be able to understand what does mean for confidence intervals or hypothesis testing, right? So because those samples are essentially random variables, this time you observe its value could be 0.7, next time could be 0.6. That's how the randomness comes from. And then to estimate, oh, sorry. To estimate, what's wrong with this? Okay. To estimate some parameter of the distribution like mean, you're gonna calculate some function over those samples, right? Which we call statistics. So statistics are essentially a function over a set of RID, random variables, right? So that means the statistics itself is also random variable, like sample mean, sample variance, they're all random variables. So if you use a random variable to estimate some unknown parameters of the distribution, there could be some uncertainty, right? So that brings the problem. What is the unbiased estimator and what is biased estimator? Okay. For unbiased estimator, it means like if you take expectation of your estimation for the statistics, the expectation exactly the parameters, then it's called unbiased. Other basis says that, okay, although I know that I just do one estimation, it won't be exactly right? But if I just do it many, many times, I take the average, it will get closer and closer and finally converge to the ground truth. That's the intuition of the unbiased estimation. And for the biased estimation, unfortunately, even you do this like numerous times, it won't converge exactly right to the ground truth. There's always some gap. That is called unbiased estimation. And based upon that, we can build up our confidence intervals. Remember, confidence interval is used to give some actual uncertainty estimate for some model parameters like mean, like variance, right? And the truth is that the model parameters are not random. The confidence intervals themselves are random. So basically, you do some kind of experiments, you calculate confidence intervals. This time it will be here, and next time it could be here, and third time could be here. Right? It is moving along with your experiments. and measurement procedure. So just keep that in mind. Okay, so we'll give a very quick overview of what we have discussed, but I believe the most effective way is just to walk through the slides we have discussed before, and it won't. Our lecture slides are not lengthy, and it won't take too much time. But it will help you like effectively walk through the topics we have discussed, and then you can do some kind of practice, look into this practice final exam problems, and say if you can solve those problems like very easily. Questions so far? Great. So let us look at those experiments, right? So I'm not gonna calculate the details because we probably won't have time to write down every detail. But I will just tell you the idea to calculate this and what kind of concepts we test throughout those problems, because all the answers are written in this solution. You can verify it by yourself. Okay. So you see that our first problem is called the basic probability. So basic probability is just testing you. Do you know how to calculate the probability for some random events? Right? So random events are usually represented by sets, right? And you want to calculate what's the probability of that event. You just want to calculate the probability of that set, right? So the first problem here we show is that a game includes a fair 8-sided die with size labeled from, so omega is the sample space, right? And you got 8-sided die. Of course, it's not true in reality, but let us just put it as our setting, right? That means our sample space contains 8 numbers, right? 1, 2, 3, 4, 5 to 8. And look at this fair, right? Fair just means like you got equal chance to see every point up, right? So now we're looking into 3 events. A contains 2 outcomes, 3 and 6. B, 4 outcomes, 2, 3, 5, 7. C contains 5, 6, 7, 8. So the first problem is what does the conditional probability PR A given B mean in English, right? So I guess this is kind of like ask you to translate it in plain English, right? You can just say, okay, this is the probability that A happens given B happens, or condition that B happens. Right? And how do we calculate this conditional probability? So this here we just want to check whether you know the formula to calculate conditional probability. Yeah, it should be straightforward, right? Okay, so this is just we're gonna divide the joint probability of A and B by the marginal probability of B, right? It's written here. And what's the joint probability of A and B? This is A intersection with B, right? That's the joint probability. So if you look at A intersection with B, what is what consists of the event? Yeah, we see just 3, right? So what's the probability? It's just 1 over 8, right? Remember, it's a fair, it's a fair die, right? This is 1 over 8. And if you look at the probability of B, you see that it contains 4 outcomes, right? And in the sample space, it has 8 outcomes. So the probability, remember, this is a fair die. So that means the probability of B will be just 1 over 2, right? Half. And you divide them and you just calculate the ratio, which gives you 1/4. Okay. So the second problem is asking you to check whether the events C and B are independent. How to check if 2 events are independent or not? right? Using the formula we discussed in the class, right? We can look at whether the joint probability equals to the product of the marginal probabilities, right? Or you can just take a look, say whether the marginal probability equals to the conditional probability. You can use whatever you want. You just calculate the joint probability and the marginal probability of B and C and check whether the two sides are identical, right? And in this problem, the answer is yes. Okay. Questions so far? Yeah, we expect no one is gonna lose point on this kind of problems, right? It's kind of like um, some basic points that everyone should get, right? And then you can see problem C, given your answer A above, right? And let us assume the marginal probability of A happens is 1/4. The marginal probability B is is half, right? And how do we compute the probability of B given A? Remember from the first problem, right? From the A, we have already computed the conditional probability of A given B, right? So now how do we compute the probability of B given A? This is the examination of the Bayes rule, right? It's sometimes we also call Bayesian inversion probability, right? It's just a way to invert the condition, the unconditioned part, right? So you're gonna leverage this formula, right? So this is just a straightforward application of the formula. I'm gonna now return this, right? So you multiply the marginal probability of B times the conditional probability of A given B, right? Which is computed from the problem A. And then divided by the marginal probability of A, right? So we got PRA and PRB here. And then you substitute conditional probability A given B by the value calculated. And then you derive the conditional probability B given A. Question? Okay, so yeah, so this is the first problem, right? So then we kind of proceed to random variable, right? So those are talk about, okay, given you know the probability space, right? You know the sample space, you know the events, you know the probability, right? So now we map the sample space to a real space, so we get our random variables, and we want to check if you know the basic definition of our random variables and their properties like expectation, distribution, and so on. So the story of this problem is like, okay, the Utah softball team has an on-base percentage of 0.4, right? So the probability of an arbitrary batter reaches base is 0.4, right? We assume each at bat has this rate independently and consider a point in game where each of 9 batters in the starting lineup has gotten bats 3 times. So in total, we got 27 at bats, right? So the first problem is what distribution models the above scenario for the total number of times a batter gets on base, basically, gets on base. Basically, you try it 27 times, right? We're gonna assume each batter and each try is kind of independent to each other. You tried it for 27 times, and then for each trying, you get chance of 0.4 to succeed. Now I want to look at what's the total number of successes from this 27 tries. So this is typically modeled by binomial distribution, right? It's like you want to reach the base. It's like you throw the corn, right? And you succeed it's like you take analogy, right? It's like you see the heads up, right? Now you try this 27 times. It's like you flip the coin for 27 times. You want to look at how many times in total you see the heads up, right? So this is a binomial distribution. And remember, the binomial distribution has the number of trials n, and also the probability that you can succeed in each trial, right? So the n will take 27, and the probability p will take 0.4. Does it make sense? Okay. And then, given we know that the distribution, right? Distribution of the total number of times reaching the base, right? What is the expectation of this number? So here we're gonna leverage a very classical result, right? As also the trick we discussed in the class, right? So of course you can write down the probability mass function for this binomial distribution. If you could remember, so if x is the total number of times, right, a beta gets on base, right? Then x, the probability x takes k, a is equal to, you're gonna take a combination, right? N from k, right? K from n, and then you got n minus k failures and k successes, right? That is the probability mass function for binomial distribution, and you can calculate the expectation according to the definition, right? But here we're going to leverage another trick. So we know that the binomial random variable can be decomposed as a summation of a set of Bernoulli random variables. So it's like you flip the coin. Like every time you see heads, the outcome of the Bernoulli random variable is 1, otherwise 0. And then you look at the total number of the heads up, it's just the summation of all the outcomes. So same here, right? Every try, you see whether you reach the base, right? If you reach the base, you got 1, otherwise 0, right? You denote this outcome as a Bernoulli random variable, like x1, x2, x3, right? So the total number of the times you reach the base is x1 plus x2 until 27, right? And then we're gonna leverage the linearity of the expectations. So basically means like if I want to calculate expectation of x, you just do the summation of expectation of x1, expectation of x2, until expectation of x27, right? And each this x1, x2 to x27, they are Bernoulli random variables. It's just like flip the coin. You have the probability p to see the success, right? And that means every Bernoulli random variable has the same expectation. It's just the p. Remember, the Bernoulli random variable is the expectation. It's just the chance it gets 1, right? And if you feel unclear about that, just look at our slides, right? So that means you're gonna sum up like NP together. So the result is just N times P. N is number of trials, P is the chance you succeed. A beta reaches the base each time, right? And here N is 27 and P is 0.4, so we get expectation. Question? Okay, great. Okay, so the third one, let's write out the probability that the first time through the lineup that no beta reaches basis. That basically means like you try all 9 times and you fail all the time, right? So this is simply 1 minus p to the power of 9, right? Because every time you fail it for 9 times. That's one lineup, right? So it's 1 minus p to the power of 9, which is 0.629, right? Oops. solve. Okay. Okay. And then the last one for this problem is to ask what distribution models the number of at-bats until the first batter reaches base. So this is a geometric distribution, right? You can remember is geometric distribution just tell you, okay, before your first success, how many failures you're gonna have, right? So this is geometric distribution, and the probability mass for geometric distribution is 1 minus p to the power of k and p, right? So this one is just ask you if you can recall what you have discussed, right, about the geometry distribution. Okay, so problem 3, right? Problem 3 is asking us to do a little bit of calculation and verify the basic properties associated with random variables, which we call expectation and variance. So, and there are properties for sure, right? So let us look at the story. The two kids go to the library and choose some books. The first kid, the name is Xander's. Xander's number of books is described by random variable x with expectation 5 and variance 4. And the second kid name is Yolanda's number of book is described by random variable y with expectation 8. So let us look at the first problem, first sub-problem, A. If Xander goes to the library twice and Yolanda goes to the library 3 times, so what is the expectation of the total number of books they get? So yeah, Xander goes to the library twice, right? So the total number of the books Xander gets is 2x. And Yolanda goes to the library 3 times, so it's 3 times y, right? So you're taking expectations of their total number of books is just the expectation of 2x plus 3y. So here we want to ask you if you know the linearity of the expectation. So linear combination of random variables is the expectation of linear combination of random variables is the linear combination of their respective expectations. So just apply the formula here, and it's straightforward to get the value. So let's look at the second problem, B. So consider just the Xander, right? What's the variance of the number of books they get on the 2 trips, on the 2 visits to the library? So we know that the total number of the books should be 2x. Right? So now we calculate the variance of 2x. So this is just asking whether if you multiply a random variable by a constant, what's the variance? Yeah, you need to square the constant multiplied to the random variable, right? And you can show it by using definition. We haven't shown that in our class. We wouldn't do that again, right? So just multiply, you just square 2, you got a 4, and then you apply variance over x, and then the variance of x is 4, so you got the result is 16. Okay. So and where's the standard deviation of the number of books Xander gets on those 2 trips? Well, you need to know what's the relationship between variance and standard deviation, right? What's their relationship? Square root, right? Standard deviation is just the square root of the variance. So you take square root. That's it. The last one is a little bit heavy. calculate the variance of the number of books Yolanda gets on one trip, and use the discrete distribution of books listed in the table. Right? So if I present you this table, which represent the distribution or the probability mass function, right? How do you calculate the expectation? That is just look into whether you know the definition of an expectation. For discrete random variable, like suppose your distribution is px equals to k, right? Then your expectation of x is simply a weighted summation. A weighted summation of every possible value your random variable can take times the probability your random variable takes that value. Right? Yeah, yeah. So here we have 3 entries in this table. That just means like your k can take 3 values, 7, 8, and 9, right? And you just calculate expectation, meaning that it is 7 times the probability x takes 7 is 0.25 plus 8 times the probability you take 8, which is 0.5, plus 9 times the probability it takes 9, right? 0.25, which will give you 8. Right? That's the expectation. And once you have the expectation, then you calculate the variance. Right? The variance is simply just the expectation of y minus the expectation take square, right? So it's the same calculation procedure. Question? Okay. Okay. So then the next problem is moving our topic to the joint probability distribution, right? We just talk about the relationship between 2 random variables or multiple random variables, right? So imagine that, okay, you're given a joint probability mass function for 2 random variables, x and y, right? And if x, y are both discrete, then their joint PMF can be represented by a table, right? And you could see like, okay, every entry of this table just represents the probability for a particular pair of x, y values, right? So now let us look at the first problem, right? What's the probability that x takes 3 and y takes 2? To answer the question, you just need to look into the table, right? You just need to find out the entry which corresponds to x equals to 3 and y equals to 2, which is 0.25. And then how do we compute the conditional probability of x equals to 4 given y equals to 1? This is to check whether you know the formula to compute the conditional probability, right? And what you need to do is just write out the form, right? I don't need to rewrite it again. It's here, right? You need to divide the joint probability that x takes 4 and y takes 1 by the marginal probability y takes 1. So the joint probability x takes 4 or y equals to 1, you can find it here, right? 0.25. Then how do we compute the marginal probability of y equals to 1? How to do that? Yeah, sum the column, right? So if you want to look at marginal probability, you just sum the column which correspond y equals to 1, right? Which is 0.25 or 0.2 plus 0.25, right? And eventually get the result here. Right? And third problem, write down the marginal probability distribution for y as a table. So we just extend what we're just doing, right? If you want to calculate marginal probability distribution for y, you just adds up all the rows, right? So y equals to 1, the marginal probability, you need to add up the first column. And for y equals to 2, you need to add up the second column. Right? That gives you the result here. And last one is asked you to check whether the random variable x and y are independent. Again, we can leverage the formula, right? So we can check whether the joint probability of x and y equals to the marginal probability of x multiplying with the marginal probability of y. But here, we need to be very careful because for random variable, it's not like random events. For random variable, you need to make sure for every possible values of x, y, this equation holds. If you can find any pair of x, y value to break this equation, then x, y are not independent. So you need to check, right? You need to check all possible combination of x and y. And for every possible combination of x, y, if this equation holds, and then we could see x, y are independent. So this is different from the random events, because for random events, you just need to calculate the probability of the two events, the chance they jointly happen and the chance they happen individually. So in this case, we can find one case when x is 3 and 4 equals to 1, this equation does not hold. Then we just stop and just say, okay, x, y are not independent to each other. Question? Everyone feels comfortable? Yeah, if you feel comfortable, you don't have any problem. You won't have problem in final exam. Yeah. Okay. Oops. So these are talking about the concepts about statistics and sampling. So consider n RID samples x1 to xn, and they're all like uniform random variables between 0 and 1. So the expectation of each random variable is 0.5, the variance 1 over 12. And let us define sample mean, which is average of this n RID random variables. So the first problem is, what does RID stand for? And you should write it out, right? Independently and identically distributed. Or you can say identically and independently distributed, doesn't matter, right? But you need to know what's the meaning, right? And the second question is, what is the expected value of the sample mean? What's that? Yeah, we emphasize this a lot, right? If you take the average of RID samples, it mean doesn't change. The expectation of the sample mean is the same as the expectation of every RID random variable. So it doesn't change. You can show that directly by the definition, right? If you take expectation of the sample mean, you're just taking an expectation over this average, right? By the linearity of the expectation, it just means like you just take expectation of every random variable and then average them. Okay. So for every random variable, their RID, right? So their expectation is the same, which is 0.5. So their average will also 0.5. So this is a very important conclusion, which we have emphasized like many times. So please keep it in mind. So the third question, what is the variance of the sample mean? Right? It's now expecting what's the variance of sample mean. Right? This is some conclusion you should be aware as well. The variance will get shrink as compared to the random variables that you average. And this can also be proved through the definition. We're not going to do that again, right? But just keep in mind, if you average n ID random variables, then your variance will be shrink by n. So it is n over is variance of each individual random variable divided by n. And the variance is 1 over 12 for each individual ID random variable. So the variance of the sample mean will 1 over 12 divided by n. Okay. Okay. As n gets larger, does the standard deviation of the sample mean get larger or smaller? This one is a direct follow-up of the problem C. Right? So we see the standard deviation is just the square root of the variance, right? And the variance of sample mean is just the variance of each xi divided by n, right? So standard deviation is square root of it. So you know that the standard deviation of sample mean is the standard deviation of each xi, which is square root of 1 over 12 and divided by square root of n. So you see that when n gets larger, remember square root n is on the denominator, right? So that basically means like your standard deviation will get smaller and smaller. Okay. Question? Okay, great. Okay. So let us look at the sixth problem. Right. So this talk about how to use statistics to perform like estimation and what is bias and what's variance and so on, right? So consider an RID random sample. We got n RID random variables actually. They're all from the Gaussian distribution with some mean mu and variance sigma square. And we calculate the sample mean, which is just the average of these NID random variables, and let sample variance. So please keep in mind what's the form of sample variance. You calculate this summation of the square difference between each xi and the sample mean, and then you divide the sum by n minus 1. Remember, it's divided by n minus 1, not n. This is to guarantee that Sn square is an unbiased estimate of the variance sigma square. So if you could remember, we try to show that why this is unbiased estimate. Okay, so let us construct the two statistics. So the first statistics is the sample mean plus the sample variance. So we call it mu1 hat. So we use mu1 hat to estimate mu, which is the mean of the Gaussian. We want to ask whether mu1 hat is an unbiased estimator for mu. This is to check us whether we know the unbiasedness, the definition, right? The definition is that, okay, I'm going to take expectation of mu1 hat. Remember, the statistics is always random variable. So you can take, of course, you can take expectation, right? If your expectation of your statistics is exactly what you approximate, you estimate, then your statistics is an unbiased estimator, right? So when we take expectation over mu hat, according to the linearity of expectation, it can be written as expectation of sample mean plus expectation of Sn squared, right? The sample variance. The expectation of sample mean is mu. Right? This is a conclusion. We know we just obtained, right? And the expectation of sample variance is the variance over n. So see that this is different from the sample, different from the true expectation mu. So it is unbiased. Does it make sense? Okay. So let us look at the second problem, right? We define a second statistics, mu2 hat, which is simply x1. You got n ideal random variables, x1, x2, until xn, right? Now I just pick up the first random variable, x1, as my estimator. And I want to use mu2 hat to estimate mu. The question is whether mu2 hat is unbiased. Again, we just verify through the definition, right? We just take a look at expectation of mu2 hat, which just the expectation of x1, which is mu. So you see, its expectation is exactly, it approximates. So mu2 hat is unbiased estimator. Okay, let's rest for a few minutes, and then I'll finish the remaining, I think, 1.5 problems. No, it's yeah, it's in Canvas. Oh, okay. Yeah, you don't download the answers. It's in Canvas announcement. Oh, okay. Yeah, yeah. If you want to take a look here, it's fine. Okay. Okay. Mhm. Okay, let us continue. So the third problem, which how to say, like for the third and fourth problems, don't worry. If you don't know how to calculate that, it's fine. It won't be the exam will be not be that hard because it's the computation of this is not a trivial thing. It just want to give you a sense that if you want to look into whether you know the efficiency of the estimator. So the problem C is asking what's the efficiency of an estimator is determined by its variance, right? So the smaller the better. So basically you want to look at what's the variance of your statistics. And for the mu1 hat, the variance will be, the mu1 hat is defined as the sample mean plus the sample variance, right? So you just need to calculate the variance of sample mean plus sample variance, which is the variance of sample mean plus samples variance of sample variance, and the covariance between sample mean and variance, right? So this guy is not very easy to compute, and don't worry, you won't be you won't see the same problem or similar level problem. But just to give you a sense, this variance will be proportional to 1 over n. Something like, say, something like alpha over 1 over n. So then we look into the problem D, right? So as n goes to infinity, for mu1 hat, mu2 hat, there's two estimators, two statistics, right? Which one is more efficient? For mu1 hat, we know that the form of the variance will be look like 1 over n times some alpha or some constant, right? And when n goes to infinity, the variance will goes to 0, right? Because n is going to larger and larger and is in the denominator. And for mu2 hat, remember, mu2 hat is defined as x1. There's not any average, it's just to pick up the first random variable in your sample. So the variance is constant, which is just a sigma square, right? No matter how you increase n, right? So that basically means like when n goes to infinity, the variance of mu2 hat is simply sigma square is bigger than 0, bigger than 0. So for comparison, of course, in the limit, the variance of mu1 hat is much smaller because 0, right, than the variance of mu2 hat. So that means mu1 hat is more efficient than mu2 hat. So just keeping in mind, what does it mean for efficiency of a estimator? We need to check the variance of the estimator. Question? Okay. Okay. Problem 7 is about confidence intervals. So we consider a random sample of size n. Basically, we got x1, x2 until xn, where n is 100. Right? Those random variables are ID. And we denote the mean of those ID random variables as mu, and assume that we know the variance, which is 4. Then the first problem, like problem A, is to ask you to write down an unbiased estimator for mu that uses all 100 random variables. Of course, we're going to choose the sample mean. Right? And if you look into the comments in this square bracket, right, it should be highly efficient and approach a normal distribution limit. You should associate with the sample mean. Why? Because the central limit theory tells us the average of ID random variables will approximately go to Gaussian distribution as n gets larger and larger, right? So that is a hint telling you, okay, you're going to use sample mean. Okay. So The second problem, what's the standard deviation of the sample mean, our estimated mu hat? And sample mean is variance is the variance of the original random variables divided by n, right? So you got 100 random variables, so it is 4 by 100, 1 over 50, 1 over 25. Third question, how do we use the information so far to construct a 99% confidence interval of mu? And this is nothing but just leverage the formula we introduced in the class, right? So if you want to find the confidence interval 1 minus alpha percent, right? For the case that you know the variance, the confidence interval will be mu hat plus or minus, right, the critical value for the standard normal distribution, right? Alpha over 2 times the standard deviation divided by the square root of sample size n, right? So just apply the formula and be sure you know the meaning of the critical value, right? The critical value for a distribution just means that, okay, suppose this is my critical value, right? This just means that the probability of the random variable respect this distribution bigger than this critical value is alpha over 2. And now we know that we want 99% confidence interval. That means alpha is simply 0.01, right? And then your critical value is listed here because z half alpha, which is 0.005, which is given by here. And then you just substitute those values into our formula to construct the confidence interval. So I got a question. What if you don't know the variance? How do you construct the confidence interval? Right. You don't know the variance is 4 here. You have no idea. But I still want to say, I'm going to still use the sample mean to estimate the expectation, right? But you don't know the variance of your random variable. How do you construct confidence interval? Yes, exactly, right? So remember, we cannot duplicate this problem, right? If we are asked, probably we're going to use a student t distribution, right? In that case, you're going to replace the standard deviation by the square root of the sample variance, right? We're going to use sample variance to estimate the standard deviation, not standard, the variance, and then take square root as the estimation of the standard deviation. And then the critical value now is not for standard normal, right? It's for the standard student t distribution with degree of freedom n minus 1. Right? And of course, we're going to give you some values here, and you pick up. Right? So make sure you understand the meaning of the formula we use to construct the confidence intervals. Question? Great. So there's one last problem. It's called hypothesis testing, but I think because we won't cover this problem, so it's totally optional for you to look into that. And that's it. And thanks for your participation of this class and a wonderful journey with you guys throughout this semester. I hope everyone will have like good summer and great summer and succeed in your final. Hey, yeah, let's stop here today.